Excellent. Thank you. So first of all, thank you, Jacob, for organizing this workshop and the series, generally speaking. And I appreciate being invited. And thank you to the audience. It's exciting to be able to share some of these ideas with you. The talk will be a little bit more on the historical, philosophical side, but hopefully there'll be some interesting things. Basically, the general topic that I'm interested in concerns the nature and role of idealizations in science. And there are two caveats that I'd like to sort of start with. The first is that I take the case study that I'm going to be talking about today to concern infinite idealizations in physics, but the morals are supposed to generalize to just any interesting idealization in the sciences, generally speaking. And the second caveat is that by idealizations, I mean something broadly construed. So I'm not going to distinguish between idealization, abstraction, approximation, friction, metaphor, thought experiments, and so on, as other philosophers do, like Patricia just did. Now, the starting point concerns the following question. Do idealizations play a substantive role in science? And what I mean by substantive will hopefully become a little clearer as I worked through trying to answer this question. Now, given that our theories, our laws, models, and so on are idealized to some extent, one would expect that our explanations are as well. And so one way somebody can answer this question is say, yes, of course, idealizations are essential for scientific explanation. In the philosophy of physics literature, I think people like Elisa Bokelich and Robert Batterman have defended something along the lines of this view. But they've received some pushback because to many, the idea that some actual facts about the world are somehow explained by things that are not strictly speaking true is rather counterintuitive. And so people say, no, idealizations are there to make intractable problems tractable. The slogan is that they make the math easier. They are there to simplify and for convenience purposes. Perhaps they highlight the difference makers, the things in the world, the factors that do bring about the phenomenon of interest by abstracting away irrelevant details. And we can understand why we need idealizations. There's no big mystery here. The real world is complex and human beings are cognitively limited, and so we have to idealize. But the constraint is a pragmatic one. Something that I've been wondering about is whether there's something along the lines of a midway position between these two camps. And I think there's various ways to develop this idea. And today I want to talk about one way of developing it via the notion of scientific understanding. By understanding, I mean something that is a matter of degree, so it's going to vary in breadth and depth, and is perhaps a little more flexible than our notions of explanation, since it seems to be a little more subject dependent to some extent. Now, there's a literature and philosophy on scientific understanding, and also there people are arguing about idealizations. Factivists tell us that idealizations are not so important and may be dispensable. Non-factivists tell us idealizations are really important and perhaps indispensable for understanding. Interestingly, though, when you see how idealizations enter the discussion in the first place, people are saying similar things. So let me give you an example. Emily Sullivan and Kareem Khalifa say, I'm sorry, I need to close the pictures here. Idealizations merely alleviate the inconveniences required to use more accurate representations, either by simplifying calculations or by highlighting features that would otherwise be more difficult to spot. And this is a kind of factivist account of idealizations in the context of understanding. But even somebody who I take to be in the non-factivist camp, like Angela Potocznik, says idealizations are used to set aside complicating factors, i.e. simplify, to help scientists discern causal patterns they are primarily interested in. In other words, highlight features of the world that would be difficult to spot. And what I'm wondering is, can it be the case that idealizations are doing more than just this, right? More than just simplifying or offering convenience? And so my hope here is to identify a positive role for idealizations to play in understanding. In other words, we'll gain understanding not in spite of idealization, but in virtue of idealization. And that sentence, the first time I heard someone speaking like that is Angela Potocznik. And so I give her credit for that idea, and other folks that have worked on such issues. Nevertheless, I'm going to try to develop it in a bit of a different way. So here's the basic idea. It seems to me that if we look at, for example, historical controversies in science, part of the way that we come to have scientific understanding of theories and models and what phenomena we're trying to explain in the first place is by conducting some modal reasoning. In other words, we're thinking not just about the actual world, but about various possible worlds, possible scenarios, possible situations, according to our theories and models and so on. Some of these possible situations, I claim, are most naturally construed as idealizations. Why? Well, they concern a perfectly symmetrical and frictionless dome with curvature at the apex that diverges. And this object arises to highlight how Newtonian mechanics is indeterministic. Or they concern a dynamically exactly two-dimensional system. And the goal here is to show that the representational structure of quantum mechanics is richer than we might have thought in 3 dimensions. Or the case study that I'll talk about today, we consider things like an infinitely long and absolutely impenetrable cylindrical solenoid. These all seem like idealizations. And so here's an attempt to articulate the basic idea. Accounts of scientific understanding ought to track scientific practice and debate. And the magnetic Aeronaut-Bohm effect case study, which I'll talk about today, shows that there are possible but non-actual worlds according to quantum mechanics, naturally construed as idealizations, that are important for understanding both quantum mechanics, what I'll call understanding with, and what the AB effect actually is in the first place, or is ostensibly supposed to be in the first place, what I'll call understanding what. As far as the motivation here, there's a kind of basic motivation where we want to understand how science works and have a story to tell about the role of idealizations. And especially if we think about, say, communicating with the public, we need to have a story to tell about why science appeals to lies all over the place in the form of idealizations, abstractions, etc. But at the same time gets at the truth somehow, or something comparable to that. However, for this talk today, more specific motivation has to do with trying to take seriously and do justice to the way John Ehrman thinks about the Aeronaut-Bohm effect, and I'm aligned in thinking about the Aeronaut-Bohm effect in the same way. And so he says, the center of interest in the Aeronaut-Bohm effect case study is on effects that should, according to theory, be exhibited by a fictional system. The goal of studying such effects is to illuminate the foundations of theory and its relationship to predecessor and competing theories. So what I'd like to do today is try to flesh that out a little bit and just start the connection with the understanding literature. What I won't get to, and as part of a larger project, is really to flesh out today's suggestions and morals with respect to the scientific understanding literature. And so what I have is something along the lines of friendly amendments to accounts of understanding. All right, so I'll talk a little bit about the Aeronaut-Bohm effect, and then I'll talk about this concept of understanding a theory, understanding within the context of the historical controversy. If there's time, I'll go back to talking about what the AB effect is supposed to be in the first place, and then conclude. All right. So what is the magnetic Aeronaut-Bohm effect? The usual setup is as follows. We're asked to consider a double slit experiment with electrons. We know that this will give rise to an interference pattern. And then the following question arises. What happens if we were to add an infinitely long and absolutely impenetrable solenoid between the double slitted screen and the observation screen, and then turn it on? Now, since we can't do this exact experiment in the laboratory, the natural place to turn to answer this question is to theory. And so we can ask, from the classical perspective, what happens? Well, we stipulated certain idealizations are in place, that the magnetic field exists within the solenoid. while the beam of electrons is outside the solenoid, and their two are causally disconnected. And so we don't expect in the classical case for anything to happen at all. However, you can ask about the quantum case, and we know both theoretically and also from laboratory experiments that something does happen, the interference pattern is shifted. In 1959, Yakir Aronov and David Bohm considered the scenario that we talked about and derived the shift in interference pattern. Physical Review counts over 3,000 citations. This is an important paper for the foundations of physics, it's claimed. And certainly philosophers of physics have paid attention over the last 30 years or so to the effect and various interpretations of it. What's interesting again is that there are certain conspicuous idealizations that arise in this scenario. And let me just state them explicitly. This is a variant of what Aeronaut and Bohm actually assumed. The cylindrical solenoid is assumed to be infinitely long. When the solenoid is turned on, the magnetic field generated is completely contained within it. So as it's sort of starting, it's not that the magnetic field spills to the outside. The solenoid is absolutely impenetrable, so that the probability of finding an external electron in the region inside the solenoid is exactly zero. Not approximately or effectively zero, but exactly zero. These idealizations together have the consequence that the magnetic field is completely shielded from the beam of electrons and vice versa in the idealized scenario. So what did Aeronaut and Bohm actually do? They started with the Hamiltonian for a quantum particle in classical electromagnetic fields. This is just the momentum operator and the vector potential operator. And they provided a kind of semi-classical approximation for the total wave packet when the solenoid is on. The approximation is as follows. You assume that one part of this wave packet, psi1, the exact solution to the Schrodinger dynamics when the solenoid is turned on is going to be well approximated by the exact solution to the dynamics with the solenoid turned off, multiplied by a phase factor. And the same thing for psi2. The upshot is that the overall wave packet picks up a relative phase factor, which gives rise to this shifted interference pattern, this little amount delta x, that is proportional to the magnetic flux through the solenoid. The assumption known as the Aeronaut-Bohm ansatz was justified basically 50 years after the effect for experiments with the toroidal solenoid by Ballesteros and Weather. Basically, they provide rigorous error bounds that shows that high velocity Gaussian wave packets make the assumption valid to a high degree. Of course, infinitely repulsive barriers, Magny and Vosgers remind us, do not exist in reality. To my mind, this suggests that there's two ways of thinking about the referent of the AB effect, what it refers to. We could be talking about the sort of idealized theoretical effect, as I described it, or the physical effect that actually manifests in the laboratory. The idealized, abstract, fictional, theoretical AB effect, which makes use of idealizations and is talked about in various authoritative sources, is such that a strictly null intersection between the electron configuration space and the region of space where the magnetic field is non-zero is a defining condition of the effect, of the idealized effect. However, Aeronaut and Bohm were clear at the start that this is not just some idealized effect, it's a physical effect that manifests in the world. It was confirmed in experiments as early as 1960, and by 1986, the large majority of the physics community sort of came around to admit that there's a physical Aeronaut-Bohm effect. So in sum, there's an idealized AB effect, there's the physical AB effect, and I'm talking about the AB effect narrowly construed as a shift in interference pattern. I'll talk about a more broadly construed later on. All right, so talking a little bit about understanding width. Michael Strevens makes a distinction between understanding why some phenomenon occurs, like why an interference pattern was shifted, and understanding a theory itself. He says, To understand a theory in this new sense is to be able to use the theory to explain a range of phenomena. And there are other such accounts. Still, I think that if we reflect on the historical controversy surrounding the Aronoff-Bohm effect, it suggests that understanding a theory like quantum mechanics goes over and above just explaining different phenomena with quantum mechanics. I think that it suggests that understanding a theory also involves navigating the theory's modal structure, what it says about non-actual but possible worlds and situations, scenarios, in order to make salient certain inter-theoretic relations and shed light on foundational issues, such as, is the theory deterministic, indeterministic, local, non-local, and in what sense? So the story that I want to tell you now is how the AB effect controversy suggests thinking about understanding a theory in this manner. All right. So Aronoff and Bohm come out with this paper in 1959. 1960, there's already some confirmation, and yet it is met by some people with skepticism. Idealizations were at the front and center of the debate, and I'll stress that with various quotes, with at least 4 related issues. So these are 4 intermingled issues that were part of what was debated. Excuse me. First, people were asking, is the AB effect a real physical effect? Has it actually been confirmed? They were also wondering about the causal mechanistic basis of the effect and whatever foundational implications are supposed to arise. And I think if we just kind of take a step back from everything, there is a question about what is the AB effect really supposed to be in the first place? I'll give you some examples that are supposed to sort of act as evidence to the effect that this is the way that idealizations were used in the controversy. So starting with Strozzi and Whiteman, they say, how can one understand the Aronoff-Bohm paradoxes? So for them, it's not effects or an effect yet, it's just a paradox. The explanation is that the description of Aronoff and Bohm is over-idealized at a decisive point. The solution of the Schrodinger equation always has a tail which runs into the region of a non-vanishing field. The tail runs into the solenoid. And that field, by purely local, manifestly gauge invariant action, referring here to the hydrodynamical reformulation of quantum mechanics, produces the effect. So we see right at the start, questions about the nature and reality or confirmation of the physical effect arose in light of the idealizations involved in sort of characterizing the idealized effect. In their paper titled Non-Existence of the Aronoff-Bohm Effect, Bocchieri and Loinger argued that the AB effect has a purely mathematical origin and that their analysis leave no room for effects of the kind of Aronoff and Bohm. Basically, their idea was that if we work with the right type of vector potential, we can gauge away the effect. In reply, Klein, Bohm, and Haley defended Aronoff and Bohm, noted that if the vector potential is not continuously differentiable, Stokes' theorem doesn't apply, and so you can't gauge the effect away. In any case, issues such as whether there's an AB effect if the infinite solenoid is, as Aronoff and Bohm assume, absolutely impenetrable, were at the front and center of the debate. So again, questioning the nature and reality of the debate in light of the idealized effect. Here's an example. Bocchieri and Loinger argued that if the solenoid is turned on first and a potential barrier is subsequently allowed to become infinite, an AB effect will be observed. But if the effect arises from the penetration of a particle into the region in which the magnetic field is non-zero during the time in which the potential barrier is still finite. The effect arises while the potential barrier is still finite. On the other hand, if one were to imagine that an impenetrable barrier had somehow erected first and that the solenoid was turned on later, no AB effect would be observed. So it's interesting. They're saying there's 2 idealized scenarios, and they're arguing about what quantum mechanics predicts regarding these idealized scenarios. By 1980, Roy came with basically a kind of no-go theorem for any physical AB effect. He argued, I show under standard continuity conditions that no effect of inaccessible field, so a completely shielded magnetic field, can exist if the vector potential satisfies a condition proposed here. The condition is satisfied in actual Aeronaut-Bohm effect, namely, the solenoid has to be finite. However, the theorem that Roy proved, although it's applicable to a cylindrical solenoid, it's not applicable to a toroidal solenoid. And so the idealized Aeronaut-Bohm effect here would be the toroidal solenoid is absolutely impenetrable to the electron, and the magnetic flux is wholly contained inside. Theorem does not apply to that situation, and Tonomura used such toroidal solenoids to confirm the Aeronaut-Bohm effect in the laboratory. Bocchieri and Langueur were not convinced. They say the internal magnetic field of the impenetrable torus does not produce any physical effect. If anything were observed, this would be due to an imperfect impenetrability or to the existence of stray fields as actually exist in reality. We shall show that the experiments of these authors in a later paper, they say, are correctly interpreted by taking into account the action of the Lorentz force on the portion of the wave which penetrates the magnetic field. Accordingly, no experimental proof of the Aeronaut-Bohm effect has been given by this Tokyo group. So they're saying, look, if there is an interaction between the beam of the electron and magnetic field, then we'll see a Lorentz force, and that's going to account for the shift in interference pattern. So what does Tonomura do? They achieve an experimental realization that's even closer to the ideal. Capras and others further confirm the effect's purely quantum mechanical origin, namely that there is an absence of forces. But Boyer criticizes the experiment, saying it's due to a classical electromagnetic lag effect, and rejects the idea that there's a kind of purely quantum origin to the effect, and so on. And so here's what I think is a nice summary of the controversy by Tonomura. He says, the most controversial point in the dispute over experimental evidence for the AB effect has been whether or not the interference shift would be observed when both the electron intensity and magnetic field were extremely small in the region of overlap. Since experimental realization of absolutely zero field is impossible, the continuity of physical phenomena and the transition from negligibly small field to zero field should be accepted, instead of perpetual demands for the ideal. What I take Tonomura to be suggesting here is that we've been getting closer and closer to the ideal. At some point in time, we need to make an inductive leap and say, if we were able to do the idealized experiment, we'd get exactly what quantum mechanics predicts. And it, in this sense, sheds light on why the controversy arose. It's just very difficult to answer the following questions. How can experiments on actual systems serve to confirm the predictions of a theory for the behavior of a fictional system? What conditions must an actual world apparatus satisfy in order to produce confirmation of the AB predictions for the fictional apparatus? So this is in the way of telling a story about why idealizations are sort of front and center of this debate. However, right at the start, the entire dialectical structure of the Aeronaut-Bohm paper suggested that the causal mechanistic basis and the comparison between quantum and classical physics was key. Here's what they say. They say, in classical mechanics, potentials have been regarded as purely mathematical auxiliaries, while the field quantities were thought to have direct physical meaning. In quantum theory, an electron can be influenced by the potentials, even if all the field regions are excluded from it. And then it would therefore seem natural to suggest that the fundamental physical entities are the potentials. And so we see here why the idealization is so important. It's only in the idealized case that all the field regions are excluded from it. This highlights the different structure between quantum and classical theory. And it also puts forth a conjecture that was very problematic. They seem to suggest that a defining characteristic of the Aeronaut-Bohm effect is that it comes about somehow through the vector potential. And this received a lot of pushback. Magny and Valsgris summarize, they say, finally, the reader might wish that a definite answer be given to the Vex question about the existence or non-existence of the Aeronaut-Bohm effect. In order to answer it, we have split the question into two. If, under the name of the Aeronaut-Bohm effect, a shifting and interference pattern is meant, then our answer is that at any rate, the Schrodinger equation leads exactly to this prediction. So far, so good. If, on the other hand, what is meant is a shifting due to an independent effect of the vector potential, then our answer is no. There is no such thing coming from the Schrodinger equation. So we see how part of the controversy revolved around what the Aeronaut-Bohm effect is supposed to be in the first place. And of course, this is intermingled with its causal mechanistic basis if you take that to be a defining feature. I'll say a little bit more about that, but first a short interlude. It turns out that there's different interpretive options with respect to the Aeronaut-Bohm effect. You may think that the magnetic fields are somehow bringing about the effect, and in the completely shielded scenario, the field is acting where it's not, so it's acting non-locally or non-separably. You may think that the potentials are giving rise to the effect, and that seems to have the implication that quantum mechanics is even more indeterministic than one would think. But there's many other interpretive options, restoring locality via other field-like entities, talking about holonomies. Lev Weidman and David Wallace have research interpretations, which I take to be more deflationary in terms of foundational consequences. In any case, I'm not interested in entering this particular debate, but rather noting what the Aeronaut-Bohm effect is supposed to be in the first place is part of what the controversy is about. And idealizations played a role in giving us a kind of understanding of that, or so I will suggest. Namely, when we talk about the AB effect, do we mean an effect that is due to a completely shielded magnetic field or flux, or something due to the potential? Is it quantum mechanical in origin, or is there a classical counterpart? Is it topological, dynamical, and so on? All right, so back to understanding a theory. The idealized AB effect, I think, makes salient the radical different structure of quantum and classical mechanics via their predictions about the behavior of an electron beam in the vicinity of a completely shielded magnetic field. This is without making a commitment to a particular interpretation, so on the face of it. The idealizations, I don't think, are appealed to in order to simplify things. Right? There are plenty of idealizations that are appealed to in order to simplify things, many of which are not spoken about, but this is not an example of that, I don't think. Nor are they primarily used to flag difference makers, the relevant factors, by abstracting away irrelevant detail for the empirical manifestation of the AB effect. So the suggestion is as follows. The role of idealization here is to afford a deeper understanding of theory by, again, navigating its modal structure and making salient those intertheoretic relations and foundational issues that are of importance to us in terms of understanding the theory. Okay. What I want to talk about now a little bit is this notion of understanding what. So just basically understanding a theory and understanding a phenomena in light of a theory comes apart from understanding phenomenon itself. This is something that's been stressed in the scientific understanding literature by various people. Philosophers call this is one version of objectual understanding. The example is as follows. One may understand phlogiston theory, but not understand combustion and vice versa. And you can pick your favorite superseded theory and substitute for the example. Now that seems right, but I also think that it's perhaps a little naive because it isn't always clear what the phenomenon to be understood is in the first place in such a theory-independent manner. This is clear from the Aeronaut-Bohm effect. Are we talking about a shift because of the Schrodinger equation or something that's due to the vector potential and so on? So if standard characterizations give rise to the idealized Aeronaut-Bohm effect, what is the physical AB effect supposed to be? Now, I don't have anything along the lines of sort of technical characterization that's supposed to be novel or anything of the sort. I'm asking the question more from a kind of conceptual point of view, more from the kind of perspective of the starting point. Tentative suggestion, the physical AB effect is the physical concrete counterpart to the idealized AB effect when we de-idealize away. In order to make this a little more substantive, we need to say some more. We need to show that there are certain rigorous results that support the idea that what we're conforming in the laboratory is the sort of physical counterpart of the idealized effect. So an example of such a result is a paper by De Oliveira and Pereira, where they start with a Hamiltonian that's more realistic. It corresponds to a solenoid with finite length and a finite potential barrier. And they show that as you take certain limits, this particular realistic Hamiltonian converges to the Aeronaut-Bohm Hamiltonian. In any case, this suggests that idealizations afford understanding of what the physical Aeronaut-Bohm effect is supposed to be in the first place. But idealizations are dispensable, and so why not just say the physical AB effect is just a shift in interference pattern due to a partially shielded magnetic field? Well, if the magnetic field is partially shielded, there will be an interference pattern also in the classical context. Here we see the interference pattern with no magnetic field, here with the magnetic field that interacts with the electrons, and here with a magnetic field that doesn't interact with the electrons, right? So this is supposed to be the Aeronaut-Bohm effect. In other words, in the idealized case, the difference is categorical. Either there is this novel quantum effect or there's no effect. In the non-idealized case, the difference is a matter of degree. The shift is predicted by both quantum and classical physics. And so we may sort of revise the way we want to think about to this and say, and again, this is just sort of the starting point, a shift in interference pattern due to a partially shielded magnetic field that cannot be explained non-quantum mechanically. So we can't sort of get this behavior here by non-quantum mechanical means, let's say. However, there's a worry suggested by the historical debate, which is any shift in interference pattern due to an almost shielded magnetic field could perhaps be in some ingenious method explained away. And there are papers by Timothy Boyer who tries to do exactly that. And some folks have said the AB effect is really not a quantum mechanical effect in origin because there's a classical, there's an analog classical effect in the context of gravitational theory. In any case, perhaps you're not moved by that. And so let's go back to thinking about what the Aeronaut-Bohm effect is broadly construed and try to make the same suggestion again. Recall that the idealized AB effect comes about through these defining idealizations. However, when you implement such idealization, it has the implication that the probability of finding an electron in the solenoid is 0. And so the configuration space for the solenoid is not all of R3, but R3 with this solenoid excised. This has the technical implication that the Aeronaut-Bohm Hamiltonian is not self-adjoint nor essentially self-adjoint. It does not uniquely determine the dynamics. In other words, the idealized assumption of impenetrability implies that the electron probability current is going to have to vanish at the solenoid boundary. And this can be implemented in various ways. We can use Dirichlet boundary conditions like Aeronaut and Bohm used. This singles out a unique self-adjoint extension of the Hamiltonian, and then everything goes swimmingly. But there are other boundary conditions we could use. And in fact, it doesn't matter which boundary conditions you use for the AB effect narrowly construed, you can derive the shift in interference pattern. But it matters for the AB effect broadly construed as an experimentally verifiable systematic dependence of the behavior of electrons on the magnetic flux in situations where the electron never encounters regions where the magnetic field is non-zero, so in an idealized case. And you can see this using, for example, scattering experiments. So in a 2010 paper from De Oliveira and Pereira, they basically show that for any two different self-adjoint extensions of the original idealized Hamiltonian, you can find a set of energies that basically is going to show that the predicted differential cross-section as a function of the polar angle will be different. And they take this to imply the following. They say, to conclude, we underline that in general, our scattering results depend on the magnetic field parameter alpha, which just depends on the magnetic flux. And this is actually a confirmation of the presence of the AB effect in different self-adjoint extensions. And so broadly construed, the AB effect concerns a family of effects. And so we go back to the question, what's the AB effect supposed to be in the first place? Or the physical AB effect? Well, if we're talking about the physical AB effect, issues of formal implementation of the idealizations don't arise. We de-idealize, or now say we have a finite solenoid. The configuration space is all of R3, and this entire talk of different self-adjoint extension becomes obscured. All that is to say is that it seems to me that the idealized Aeronaut-Bohm effect, narrowly and broadly construed, affords understanding what the physical Aeronaut-Bohm effect is supposed to be in the first place. A kind of understanding that is gained in virtue instead of in spite of idealization. And notice what I have not said. I'm not saying that in order to explain what's happening in the laboratory, we need to appeal to idealizations in some sort of indispensable manner. Okay, conclusion. I think I'm doing okay on time. So I've suggested that idealizations play this positive substantive role in science via the notion of understanding, understanding a theory and understanding what an effect is in the first place. One way to continue this project, which I do in the paper, is actually apply this to particular accounts. I do want to consider an objection on behalf of folks from the scientific understanding literature. Namely, I cited some people talking about idealizations and then said, this is not the only way that idealizations do work for us. The thing is that they weren't talking about understanding a theory. They were talking about understanding why some phenomenon occurs, say, understanding the explanation of some phenomenon. Still, I think that insofar as a deeper understanding of why actual phenomena occur presupposes understanding the theory that describes the phenomenon, and perhaps, if applicable, understanding what the phenomenon is in the first place in terms of the theory, then idealizations indirectly also afford some understanding of why phenomenon occurs, right? That's a kind of deeper understanding, if you will. That is not to suggest that it isn't facts about this world that explain why things happen in the world. So for my last slide, since I've been fond of making suggestions, I'd like to throw out there another one that perhaps is going to be more relevant for discussion, especially in light of Patricia's talk. It isn't really clear to me on the face of it what, say, a boiling kettle has to do with a superconductor or a magnet that becomes, a piece of iron that becomes magnetic. All this becomes clear that there is some phenomena, say phase transitions or the universality of critical exponents. All this becomes clearer when I start thinking about the theoretical representation of what's going on here. And if that's the case, perhaps we should try to take seriously how, for example, phase transitions are characterized in theory. And as was mentioned before, they are characterized via idealizations. Right? That's not to say that idealizations are indispensable for explaining or talking about boiling kettles, but perhaps we're doing some sort of injustice to the work that they actually do in terms of bringing about understanding when we take it too much of a deflationary approach. But that's just an idea. Here are some of my references, and thank you for your time.
Thank you, Eli, for a wonderful, wonderful talk. We have time for questions. Eli, you finished a couple of minutes early, so we have more time for questions. And we'll just do a brief question period until 5 minutes before the hour, and then we'll take another break. Unless we run out of questions, in which case we'll take a slightly longer break.
I'm glad to give some of my time to Patricia, so if you want to ask her questions, you can as well. So feel free.
We still have the time at the end. So
we do still have the time at the end. So if we do run out of questions for you, Eli, then maybe we'll have an opportunity for some questions for Patricia. I see a hand from Lev first. Lev, please go ahead.
And so I will not talk about my objection to Aeronaut-Bohm effect, which is maybe of some, again, I don't know it's an idealization or not, because Aeronaut-Bohm effect source was considered classical, and if you consider quantum, then the main conclusion I think you cannot make. But until I kind of suggested to consider this idea, most of at least early references you mentioned were about this penetration of the wave inside, and I think in general in physics, when we perform an experiment, there are some things which are not exact. But we know roughly what is the scale of experiment, what is scale of the effect, what will be the size of the shift. And the size of the shift Aeronaut-Bohm effect is given by exactly this Aeronaut-Bohm phase, given by potential. And all these other effects, they cannot be of this scale. So all these papers of this kind, I think they just were mistaken, because it was noises which cannot make this effect. Of course, at that time, people thought that potential cannot be physical, and this was a revolution, and they tried to find everything. But this was just a mistake. So I think in the moment, you have theory which tells you that in particular situation, it's only effect of potential, end of story. And this was kind of a noise of disbelief. But I don't know how much it's about. I think this is the main reason of the story, not that idealization plays a role. It's Aeronaut didn't say that in the moment there will be some leakage, then the effect disappears. They understood that some leakage will slightly shift it, and this in fact happens. So the main sizes effect remain without.
Should I reply now? So yeah, I think I understand what you're saying. Perhaps some folks were mistaken, and the exact effect can't be explained away by just trying to do it by a classical means. I guess there's two thoughts here. The first is, if you follow the kind of controversy, right? And I tried to tell the type of story that John Ehrman tells and emphasizes, I think he's right about the fact that people were arguing not so much about exactly what's going on in an experiment, but whether or not the experiment is getting close enough to confirming what quantum mechanics says about the ideal. And if that's right, idealizations are at the front and center of the debate. But regarding the comment that if we try to account for what we see in experiment without taking into account the sort of quantum mechanical description, we won't be able to do so. I think fair enough. However, as I tried to emphasize, in the idealized case, it's crystal clear that there is a novel effect, because the classical picture, as I understand it, says that nothing will happen. But in the realistic case, it almost becomes kind of like, here's a quantum correction to what, you know, the classical picture gives us. And, you know, in that sense, it sort of undersells the effect as I understand it. But that's basically the suggestion.
Okay, I don't think there is much disagreement. It's still that the emphasis on Aeronaut-Bohm effect that it's when there is no field. But Aeronaut-Bohm effect exists when there is a field. You just calculate the shift using the potential and not the field. And in any, you know, people use it a lot, and this is a very efficient tool in many experiments. And they don't try to avoid the electromagnetic field in an electron. They just use the fact that there are oscillation due to the flux. So you ask physicists what's the Aeronaut effect. Today, it will say just you change the flux and you'll get phase. And then it was a revolution in thinking. This is why people really said that the effect is because of, there is no, this effect happens without field. But anyway, it's defined without field, it's defined by potential. So I don't think there is a contradiction between. Thanks.
Thank you, Lev. The next hand I have is from Joanna, and I also have a hand from Noel. Noel will go next after Joanna.
Thank you. You mentioned some philosophers who have argued that Aharonov effect reveals some kind of non-locality, and I'm curious, what are the consequences of your approach for this debate?
I don't know that there are any consequences of my approach for that debate. So I think that, again, was not entering the debate of what are the different interpretations of the Aharonov effect and what are the foundational implications. What I was suggesting is that if we look at how idealizations were actually appealed to in the historical controversy, idealization was front and center of the debate. And now what I was trying to do is make a connection between that and how we talk about understanding theory, models, and what a phenomenon is in the first place. So trying to make a little bit of a connection with how we think about understanding, given, I think, a sort of reasonable background claim, which is part and parcel of what science is in the business of, perhaps is also allowing us to understand how the world works, and so on. Of course, if you're empiricist enough, you may reject that idea.
Thanks, Joanna. Next hand I have is from Noel.
Thanks. This is a really quick question. So at the very beginning of the talk, you laid out the kind of two broad camps. One camp is, yes, idealizations are essential for explanation. And then the other one, no, they're not essential. And there's various other things. They might typically pragmatic things. And I was just a little bit surprised that highlighting or isolating difference makers fell on that side, because I would have thought naively that that's part of the explanatory game. So I guess the question is the idea there just that the difference makers are there and the idealizations just help us to see them? Or is it something deeper, like the notion of a difference maker here is supposed to be relative to an agent's understanding or an agent's theoretical description of the system, or something more deflationary like that?
So I think, I gather it will depend on the person's account. I took the way I was talking about difference makers is just, look, there's the thing that really matters, and in order to pay attention to that, we just abstract away from the irrelevant details, or perhaps the idealization allows us to sort of focus on the thing that really matters. And so I take that to be more in the camp of the dispensablist. Your second way of talking about things seems to make it a little bit more essentialist in character. I gather that when someone like Angela Potocznik talks about how idealizations let us focus on the causal patterns that really matter, she has something more in mind there. So that's why I said she is trying to find this sort of positive role for idealization. She does think that idealizations give us understanding in virtue of the idealization. Just her way of developing it is a little different from the way that I tried to do so.
Awesome, thanks.
So I have a question. Your talk reminded me of something a favorite professor of mine once told me when I was an undergraduate, that sometimes to teach physics effectively, you have to know when and how to lie correctly. And I've been rethinking that statement in light of your talk about the role played by idealizations and understanding. Because I guess in that context, his point was that idealizations can be important in learning physics. In practically every introductory course or treatment of a topic in physics, Lots of idealizations are made. The idealizations are very much not taken seriously. They're not regarded as fundamentally explanatory. They're regarded as convenient to improve what I would have said was learning, but as you pointed out, is understanding. And I guess I'm interested to hear from you about how your view on the role played by idealizations understanding is connected with learning, learning physics or learning in science more generally.
Right. Yeah. So very good. I guess idealizations can facilitate learning, pedagogy, understanding, insofar as they do lots of the things that I mentioned in the way of making intractable problems tractable, making the math easier, and so on and so forth. But that's, I was trying to tell a story about how idealizations are doing a little more for us than that. Still, the little more that they are, ostensibly doing certainly would facilitate, for example, learning what the Aeronaut effect is about. So from my very sort of naive starting point, I think that it's crystal clear in the idealized case that there's some sort of novel effect because the field is completely shielded and quantum mechanics is still predicting some effect. And that's odd, right? That seems to get at something, perhaps some sort of non-locality, et cetera. I think that it's crystal clear to see that in the idealized case. When you de-idealize, problems arise, and those problems manifested via back and forth between many physicists, as I discussed and as John Ehrman discussed.
Great, thanks. I see a hand from Samuel. Go ahead, please.
Yeah, I just wanted to follow up on Jacob's interesting question. I wonder, Eli, if you think that you could assimilate pedagogical uses within a broad understanding of understanding. The idea being like the type of understanding most of the time we talk about in philosophy of science might be referred to as the understanding of the research community, right? Where the relevant unit is kind of like the best summary of kind of like research consensus regarding whatever understanding is really about. But you might also consider, the unit of analysis not to be the research community, but individual folks, right? And so in that case, you might say that, understanding the role of idealizations for understanding plays exactly the same role. It's just that we apply it to a different unit of analysis, where we apply it to individual folks, particularly in pedagogical contexts, where the sort of thing that you were talking about is mostly where the unit of analysis is the research community or the scientific consensus regarding whatever understanding is of this subject. Does that seem like it fits with your picture, or do you think you would want to tweak that or modify it in some sort of way?
I guess I'm wondering about, so if we transition from a unit of analysis that's a community to the individual, does that fit with the kind of things that I talked about today? Is that the question, or? Yeah,
I was trying to draw like or construct another bridge from Jacob's question to your detailed insights about understanding, another way of thinking about how the connection might be made. But because you've been thinking about this much more than I have, I wanted to know what you thought about it.
Yeah, I'm not sure. I think I'd need to think about it further. I mean, there are people who have full-blown, very intricate accounts of scientific understanding, Karim Khalifa, Direct, Patochny, all these people. And, as I tried to advertise, my goal was to say, look, there's this interesting case study. And, if we take these ideas seriously, such accounts may need to be amended. Question, are the accounts applicable to just communities or individuals? I'd say they're applicable to both, but yeah, I would need to think about that more.
Thanks, Samuel. All right, so I want to thank Eli again for a wonderful talk and for everybody for their wonderful questions, so thanks again. We're going to take a brief break for everybody. We're going to take let me stop the recording.